Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Alright, step out inside, and we are now dealing in terms of trigonometry in these videos. Now, I made a video last year, it was a lecture video, not a solution guide one, a lecture video with examples on basic right triangle trigonometry, sine, cosine, tangent, and their inverses, how to find angles with them. We are going to be dealing with, in at least this video, it's a solution guide, I think 21 questions in full, really dealing with sine, not so much cosine and tangent, actually not at all that I know of, sine and inverse sine in certain ways where we use them in non-right triangles, how they have right triangles technically inside them to make these formulas exist, but to how to find the area of a triangle in a certain situation with certain values using sine, and how to find missing measures using sine. This specific section is called Law of Sines, where it's how we find missing parts, missing measures of angles and sides. But I'll start the first few problems trying to find, I'm looking at the screen, trying to find areas of some triangles here. So we'll start with that and we'll just jump straight into it. And if you want to see what that other intro to trig video looks like, I'll try and link it right down below in the description for you. Let's go ahead and get started here. In the first six, I think actually the first 8 problems, we're going to find areas of triangles, but the next 2 are a little more special, and we'll take care of it. By the way, you're going to want a calculator for this, and follow along with you might have a different calculator, but follow along with some things, some routines that I request of you to make sure that you get answers correct and not incorrect. Okay, find the area of each triangle round to the nearest tenth. Now, the formula that we're going to be dealing with here, or the idea, is that we are going to be working with 2 known sides of a triangle, not necessarily a right triangle, and something called the included angle. The included angle is the angle that is between your 2 known sides. For example, if I knew that this angle here was 30 degrees, this is not an included angle. This angle is not in between 2 known sides. I do not know the length of this side right here. But I do know these 2 sides right here, and then the angle in between. This is the included angle. So in a situation where you do have some triangle, where you have 2 known sides in the included angle, you can either put something like some theta, or I'll show you what else I'm going to do with this. The area of this triangle, without diving into a proof right now, but I'll show you a practical version of one in a sec. The area of this triangle is 1/2 times A times B times the cosine, times the sine of that angle. So 1/2 AB sine of theta, like that. So we can be using this formula straight up. I could tell you right now, just plug them in and go to work. But of course, you know me, I want to go slowly through some of the teaching bits. I want to make sure you do it right in the calculator, all that jazz. So in this situation here. Now, alternatively, because A, side length A would be opposite some angle A, which will be important for what we do later. Side length B is opposite angle B right here. That if this is angle C and side length C is opposite it, if this is angle C, you might see a lot of places show this as well, sine of C. And when we do law of cosines, if I'm able to do a video with you, then you'll definitely see me using a C instead of a theta in that scenario, only because it needs all the other side lengths involved. So either way, theta or C, the angle in between is there. So straight up, if we're using that formula here, on number 1, I know 2 side lengths here. I can refer to A as, say, 4 and B as 3, and they can be used interchangeably. A could be 3 and B could be 4. It does not matter because we are going to multiply them in the end, and multiplication is commutative. Now the angle in between is the 120, so that would be my theta or my C, what have you, 120 degrees. So we can say now in this case the area of this triangle. This is not A as in the angle opposite the side. This is A as an area. The area of this triangle is 1/2 times A times B times the sine of theta, or the sine of 120 degrees there. And, you know, sometimes it's best to even write the exact answer before doing the part in the calculator, like 1/2 of 12 is 6, so 6 times the sine of 120, like that. And later, you'll actually learn what the sine of 120 degrees is as an exact answer when we start diving deeper into some of the trig stuff. But for now, we're going to work off our calculator here. So let me go to my calculator here, and let's go and make sure. Here's going to be the important part, and if you're coming off a graphing calculator like me, and it's brand new for you, and you haven't borrowed it from a sibling, or you haven't done trig with it before, your calculator is likely defaulted to something called Radian Measures, or your other calculators may as well. Sometimes you can see it in the corner of a screen. You'll see a capital D or capital R, or you'll see it say deg for degree, or rad for radians. You want to make sure that you are in degrees for this when we use this trig stuff. Now, we will be using radians somewhere down the line, but not right now. As long as we're talking about degrees, like 120 degrees, we want to be in degrees. So you want to find a mode on your calculator. For me, it's within mode. And right here, you can see that there's a radian measure, and we have to switch it here to degree. If you're in radians, you will get a completely unrelated answer. Completely different answer. There's nothing to do with what we're doing. So my exact answer, I'm going to be doing 6 times the sine of 120. If you want to do 1/2 times 4 times 3 times sine of 120, that's fine. But 6 times the sine of 120 degrees here. We're going to round to the nearest tenth, as this thing says, and this thing is going to become approximately 5.2 square units here. They don't show the units, so I'm just going to go ahead and put a square, like u squared, like this right here. So 5.2 like that, and that is the area. And it's squared because it's area. That's what we're doing here. Okay, now in number 2, I'm going to begin with a practical approach here and kind of show you where the formula comes from, and then reapply it here, because one's a little bit different of a problem having an obtuse angle. You'll see what I mean. You'll see what I mean when I talk about this. If you want to find the area of any triangle, guys, the area of any triangle is 1/2 base times height. Now let's say that you knew some base length down here, b. The height is always perpendicular to your base like this. It's not this length here, it's not this length here, but it's this length. So not knowing that height right now in these triangles that we're looking at, sorry, area is 1/2 base times height. Not knowing the height that we have in this triangle right now, because it would have been a perpendicular distance, is something that we can try and formulate, right? It's something we can try and come up with. And we can do that using sine, because if you build this altitude right here, you're building, in essence, a right triangle. Right here, I have a right triangle with a 60-degree angle measure and a hypotenuse of 4. This length is not 3, nor is this 3 cut in half exactly. We don't know what that is, and personally, we don't need it. What we need to find is height right here, and we can use 60, not Pythagorean theorem, but we can use the 60 in trig to actually find that out. So a setup you could do, if you don't remember your formula, if you're uncertain how that works, you could go ahead and say that the sine of 60 degrees, the sine of 60 is opposite over hypotenuse. That would be h over 4. And if you multiply both sides by 4, you would get h equals 4 times the sine of 60 degrees. So this could be represented as the exact height of your triangle, this many units, this length. So this could be your height. 3 would be considered your base in this scenario. So if I wanted to do some sort of 1/2 base times height, I could say 1/2, area is 1/2 times base times height. Now, does this not look like, excuse me, this to me looks a lot like, well, if my A was in essence 3 and my B was 4 and my theta was 60 degrees, this sure looks like 1/2 A, B, sine of theta. The only difference is I don't have a parenthesis around the b right there, because it's exactly that, and that's exactly what you're doing. So there's that practical approach, actually drawing a height, representing it inside a right triangle, using sine to isolate the height variable value, and substituting it into your triangle area formula, 1/2 base times height. And that's actually what's happening. That is what's happening, and that's why it has to be the included angle. Now, this exact answer is half of 12 is 6, 6 times sine of 60, and you're going to be caught with a little surprise here when we go ahead and do this answer in the graphing calculator. So let's do 6 times sine of 60. Surely this must be half of 6 times sine of 120, right? We're going to get that answer. We're going to, oh, what did my calculator just do? I got the same exact answer. Was that correct? It actually was. So this is also approximately 5.2 square units. And you might be sitting there and wondering, why and how is it possible these two have the same area when this is a larger angle? Especially when that becomes a larger side. Well, it fills out. It angles differently, but it fills out the same. And because 60 and 120 are supplementary to each other, it also even allows for that to kind of be the same. Picture, if you will, let's see how I do this. Picture, if you will, if I drew this same exact thing, if this triangle was right here and instead the 3 was right there, I don't know if you can imagine that those have the same area right here. See, they both have that 4, and this is 60 degrees right here. These both have the same area there, right? So it's very possible. It's not like that this thing shrunk a little differently than that. But so the real question for you guys would be several-fold. Not just why are the areas the same, but how could you use this practical approach over here, and then why is the sine of 120 therefore then the same as the sine of 60? So let me try and answer it that way first, and then I'm going to go to the other ones actually relatively fast. so that we can keep moving forward. So right here, and you can advance on if you're not interested in this. So right here, the base is 3. If I considered 3 to be the same base as it was before, where would my height be? How can I draw this height perpendicularly in such a way that it matches right there? You could do this. It's kind of weird like that. What I would do is actually draw it over here. I would extend my height downward like that, and even extend the base outward like that to kind of just give me the gist of what it is I'm looking for. It's perpendicular to the base, even though the base is still just 3. It's not like it's however long this is right here. But then the question is, if I'm trying to find that height, discover it and write an equation out of it, doing the same thing as I did before, how do I do it within this triangle? And the answer is you kind of don't. You just want to relate. You want to find a way to evaluate this height. You want to find a way to evaluate this height. And the way that you do it is by using any right triangle necessary. And in this case, we have one right here. And we can still use sine as long as we know this angle. And we'll know this angle because it's the supplement of 120 degrees. This should be 60. So here, look at how the equations can be exact same. The sine of 60 degrees, sine of 60 is opposite over hypotenuse. It's h over 4. So everything is still the same. H is 4 times sine of 60, and we're right back to where we were before. So the height is represented in such a way that you can still get its height using 60 as you could 120. This goes to show that the sine of 60 is the same as sine of 120. And this will be important later down the line when we do more of this. The sine of an angle and the sine of its supplement are equal. They're equal. So 110, sine of 110 and sine of 70 are the same. Sine of 170 and sine of 10 are the same. They are all the same when it comes to that. And it's kind of nice to talk about, and that will be important for us to talk about even later in this video when we start to find missing measures of obtuse angles when we get deeper into that. So anyway, that's just another basis of how you can still get that if you wanted to from a practical approach. It just goes to show sine of an angle and supplement are the same thing, and we can move forward. Okay, and let's keep moving forward. And I'll continue to use the formula here on out if need be. So let's take a look. This is going to be area of 1/2 times A times B times sine of my theta, or C right there. So that's half of 16 is 8. 8 times sine of 60. So also some little irrational number there. I'll go and use my calculator. I'm not going to show you here. It's not too important. 6.928203203. So around 6.9 square units there. And there's my area. Moving forward, you can see that this is, at this point, going to be a little less taught and a little more just talking through these ones. I don't know how much more I need to say on some of these. The area here, my A and B, I can do half of 5 times 3 times sine of 40. I don't know exactly what sine of 40 is or whatever, but half of 15 is 7.5. I always like to get an exact answer whenever I can before I start it off. All right, let's do 7.5 times sine of 40. And again, just make sure you're in degrees. I'm getting around 4.8 square units here. All right. Number 5, and you're seeing some isosceles triangles here and there. That's neither here nor there when we talk about it, but I'm sure that you could, this would actually then split up this side in half, but you'd still need to know what the length of that side is. And when we learn law of cosines, you'll actually be able to figure out what that side length is in this situation. Okay, number 5, this is going to be area is 1/2 A times B times sine of this theta. Now remember, 130 being an obtuse angle means its supplement would be the same. The sine of 130 and the sine of 50 are actually the same value. That doesn't really matter for this problem, but I just wanted to let you know that that would work. That would be exactly, what's half of 49 here? 24.5. You might be wondering why I'm doing that. It's, for these answers, probably not the biggest thing. In fact, it's probably going to lead you to doing more things wrong. You might accidentally miscalculate that. I might have even here. I don't know. 18.8 square units. I think I'm just so used to it, either from the teaching realm or having done it so often that when you need an exact answer, if I have to use that exact answer later, like I'm not going to use this rounded answer to calculate something different if I need to. It's just embedded in me to say, let's get that exact because we can. And although this part's approximated or irrational, keep going. Now, number 6 is something I want to go back to a teaching moment with. If we worked on this, this included angle is 90 degrees. So this would be an area which is 1/2 times A times B times sine of 90. Now, I do want to write the exact answer here, especially to show you how it compares to what happens when we use the calculator. So 1/2, half of 32 is 16, so 16 times sine of 90. Now, I'm going to show you my calculator here as we go to it. Let's check out what 16 times the sine of 90 is. And it is 16. Oh, I got 16. All right, so it's 16. It's exactly 16 square units. What's that telling you? If 16 times the sine of 90 is 16, it's telling you that the sine of 90 is 1. Now, that's something we'll get into later, of course. I say later, I don't mean later today. I mean later in unit circle trigonometry things, that the sine of 90 is 1. 90 degrees is 1. But even more so, what we're telling you is you didn't have to do this part of sine of 90. If you know what's going on here, the area of a triangle is 1/2 base times height, and height is always perpendicular to base. Hey, you could have done this long before. This is a right triangle. Area is 1/2 base times height. You don't have to do any more of that, right? We didn't have to work on sine of 90. So I don't know if they're testing you with that, whatever. You're learning a little something that the sine of 90 degrees is 1, and that seems to hold merit with what we could have also done here. So we could have done a little less. Don't overdo a problem if you don't have to. Okay, number 7. What is the area of an isosceles triangle with congruent side lengths x and included angle theta? So they are just asking you to kind of write out a formula-esque, if you will. So there's no actual like answer. Isosceles triangle right here. These two are congruent to each other. They're both x. This is going to be 1/2 a times b times sine of theta, like that. So to simplify that a little bit more, we could write x squared, 1/2 x squared times sine of theta, or x squared times sine of theta over 2, something like that. That'll work out. Kind of a weird kind of question, but there's a good old breakdown. So any isosceles triangle, you could kind of write it out that way. We had a couple like this one here. I wouldn't bother. What is the area of an equilateral triangle of side length x? So in an I actually have a shape for it. In an equilateral triangle, there you go. In an equilateral triangle, all of them side length x here. Don't overthink this too much. Your included angle is 60 degrees. In an equilateral triangle, it's also equiangular. Every angle is 60-degree measure. So that x squared thing will come into play again. 1/2 a let's do this. Let's write x squared times sine of 60 over 2. Now, you're not supposed to know this yet, I guess, but the exact value for the sine of 60, it's not as a number base. Well, sort of, it's the square root of 3 over 2, and there you're going to learn this again later. It's the square root of 3 over 2. So if I plugged that in, and I don't know if this is what they want from it, so that's x squared times the square root of 3 over, and then that 2 multiplies with the other 2, so over 4, like that. That's as exact an answer as you can get to kind of give a better look at it. So I don't know, just answering the question that they have there. And yeah, there it is. All right, enough with the area. Now we're actually going to deal with what's called the law of sines. Now, the law of sines states that there is a certain proportionality among a triangle's angles and their sides opposite them in the entirety of the triangle. As in, this angle and the side opposite has some ratio that I can write that is actually equal to this angle and the side opposite and this angle and the side opposite. And it's not a direct proportionality in the sense that if I double an angle measure, then I double its side length opposite. And there's an instance where I think that'll make a lot of sense to you that wouldn't make sense. But there is one, and it involves sine. And it's such as this. And you can write this one way or the other, and I will write both. If you have a triangle, ABC, if you have a triangle, triangle A, B, C, like this. And I'm not going to dive into the why of the matter unless I absolutely have to, like the verifying the proof. And it actually is a little bit like what you saw in the previous one. You can say that the A over the sine of A, meaning the angle measure A, equals B over sine of B equals C over sine of C. Now this is a lowercase c, that's a capital C. You could also flip this over, of course, and write sine of A over A equals sine of B over B, or angle B over side length B, equals sine of angle C over side length C. Now, a couple things to these formulas. As I said, you can do one or the other. Of course, you can reciprocate them as long as they all do that. That's fine, number one. Number two, you're only going to be using two things at a time here. They don't have to use the letters A and B and such. What's important is that you write a proportion, a single equal sign with two different fractions here, and you choose one set of an angle and a side opposite that you completely know the values of, and then another one where you know at least one of the values of, or you can discover it on your own to make a formula out of. You don't want to use two things where you don't know the values at all. For example, right now, which I'll show you that we can get it, we don't yet know the angle opposite side length A, which we also don't know. So I can't solve for either of these two using the law of sines because that would be two variables in one equation. Eventually, we'll be able to do something with it using a triangle angle sum theorem. But right now, don't use it. Use two bits that you do know, and then one bit that you do know, and find that side or angle opposite. So let's go ahead and look at number 9 and see if this thing will make sense what we're going to do with it. We do know this. Okay, so this would be considered, let me put it in black. This would be considered angle A because it's opposite side length A. And this must be angle B, therefore, and I guess this is going to be considered C because that's side length C, but we know what it is. We know angle C's measure, we know side length C's measure. We're going to be using these in proportions, and they are exact values. When we find other ones, they will probably be approximated at some point, but let's use the ones that we know for sure right here. I do know angle B's measure, but if I needed to find side length B, I could use the law of sines. I can use C's angle and side length and B's angle to find B's side length. So let's use, I'm going to kind of bring this over. I'm going to kind of use these two right here. Again, it doesn't really matter how I kind of put it, but I want to put my variable on top. I think it's easier to solve for if I do, having the unknown on top, so I don't have to multiply it upward. It's already up in its own numerator. So I'm going to do B over the sine of B, and B's angle measure is 80 degrees, equals C, which is 10, side length C, over the sine of angle C, which is 50 degrees, right there. And that's my proportion that I'm writing out here. This is where we can find side length B. Now I'm going to multiply both sides by sine of 80 so that I can get B's length by itself. B is 10 times the sine of 80 degrees divided by the sine of 50 degrees. Now, you can't cancel out sines. There's nothing like that that's involved in this calculator stuff. You are literally going to calculate what this is. And I'm going to go to the graphing calculator and do exactly that. So I'll do 10 times sine of 80 divided by sine of 50. Make sure you're still in degrees for yourself. Over sine of 50. And I'm getting around 12.9. It doesn't say what's around to, but I'm getting around 12.9 units here. Okay, so 12.9 units there. Now they say find the unknown measurements, so I'm not done. This was just my first choice in what to find. Before I continue forward, let's just see if the answer makes at least some bit of sense. And for me, it's called the, I don't know what this one's specifically called. It's a part of just an essence of triangles and their angles opposite. If I have an angle measure that's 50 versus an angle measure that's 80, clearly 80 is more than 50. Well, the side length opposite 50 should be smaller than the side length opposite 80. And it is. They're not in the proportion as in if 8 is 60% more than 50, then this number should be 60% more than 10. It doesn't work that way. It works this way with the sign of the angle measures, not just the angle measures themselves. So again, I don't double in angle measure, and therefore the side length gets doubled. The side length is going to be less than double in those scenarios. There's actually an exact amount I could tell you later. But anyway, but it's more. It's more, and it should be more there. And A, we still have to find out what A's angle measure is here, and we can. A's angle measure should be 180 minus the sum of 80 plus 50. So that's 180 minus 130, which is 50 degrees in and of itself. So 50 right there. Now I'll tell you what, right now, if you know your knowledge of isosceles triangles, because that's what this is, you have a 50-degree angle measure, 50-degree angle measure, we should know right now that A's length should be 10. This is an isosceles triangle, those should be congruent, that should be 10, boom, straight up, we shouldn't have to do anything. But if you want to still work on law of sines, I'll get you set up with this by first telling you that in finding A, let's go ahead and use C's measures again. I do not want to use B only because this value is approximated. If you happen to use the exact one that's still in your calculator, be my guest, but I think you're working more than you should be to try and find that. So let's go ahead and use C's measures again as we did to try and find A in the same way that we did before. I'm going to say A over the sine of A, and that 50 degree is not inexact. That is exact how it is. Equals c over the sine of c. Now, once again, as we're setting this thing up, you may realize that both of these are dividing by the same value. So if we multiply both sides by sine of 50, what's going to happen is those sine of 50s here will effectively cancel out. You will be left with a is 10. You shouldn't be going to the calculator trying to do 10 times sine of 50 over sine of 50. Any non-zero value divided by itself is 1. A is 10 units. And this is solving the triangle. We found every single missing measure here. Even if they didn't ask us to find this unknown measurement right here, right? Because I made that up for myself. I filled that in. And these were here. We had to find these two. I needed to get this 50 in order to find it. I needed the angle measure opposite that side to find it using the law of sines. Okay, we'll see how mundane this stuff starts to get after I taught that one. It might be a little repetitive. And again, if you can do them for yourself, please do so and fast forward these as you see them, but I'll continue on forward. So number 10, in the same way, this should be my A, and this should be my B, and this should be my C there. And it looks all very same-ish as far as what we need to do and find. We still need to find that A and B, and of course this angle A. I'm going to start by finding that B the same way I did before. Let's do B over the sine of B equals C over the sine of C, like that. Multiply both sides by sine of 75. We'll get b equals 12 times the sine of 75 over the sine of 35. Trust me when I don't show you the calculator here that I'm going to get at least a value that I hope to be the same as what you get. Just make sure you close parentheses when needed by sine of 35 here. And I'm going to be getting 20.2. It's around 20.2 units there. And again, make sure that it makes some bit of sense. 75 is more than 35. 20.2 is more than 12. Notice 75 is more than double that of 35, right? If you double 35, you get 70. 12 times 2 is 24. So it's clearly it's not in a direct linear proportionality with them. I just want to just double check that, but it should be more. Just like to me how it made sense. One of my friends once told me, as I was driving them when we were in college, he was like, whatever speed limit a road is, and if there are traffic lights on it, the time that that traffic light will be yellow is 10 times less than your speed limit. So if your speed limit on a road was 30 miles per hour, the traffic light will be yellow for 3 seconds. And if it's 50 miles per hour, then your yellow light would be 5 seconds. Now, I don't know, I think we tested that once and it wasn't perfect or whatever. And it should be less than 5 seconds. 5 seconds is a long time, but 50 miles per hour, it makes sense. What he's mentioning though, the faster a road is, the faster you can go on a road, the more time you'll need to brake and, kind of do things like that. So the longer a yellow light will be. I understand that. I think that makes sense. I don't know if a 10 mile per hour road will have a 1 second yellow light though either. I don't know. There's probably some sort of equation that they use or some idea of it that really does make sense with what he meant, but I don't think it's just a 10 times linear thing. Same thing here. I think it makes sense that the side opposite angle is going to be longer because as this angle opens up, there needs more side to compensate versus a smaller angle right here and a smaller side opposite. That all makes sense. So this should be more. So, and the reason I keep saying that is because people will mess up in their calculator when it comes to what they're dividing or how they type some things in and how things switch around. So give yourself red flags if something goes wrong. And I'm calling attention to this right now because people will make mistakes on them. Okay, let's go and find angle A the same way we did before. I'm not going to write out this whole measure part, but we can figure it out. 75 plus 35 is 110. 180 minus 110 is 70. So this is 70 degrees, not an isosceles triangle in any sort of way. Let's go ahead and solve for A together. It should be pretty close to that 20.2 value, a little bit less, right? So let's go ahead and find that one. Let's do A over the sine of A. Now that we found that A equals, and let's use C again, C over sine of C. So the length of A is 12 times the sine of 70, as we multiply both sides by 70, over sine of 35. 12 times sine of 70 over sine of 30. And sine of 70 over sine of 35 is not 2 either. Hold on, I just have something wrong. Sine of 35. We're getting 19.65, so 19.7 units long right there. And yeah, that's pretty close to the 20.2, a little bit underneath, and that's exactly what we expected. something along those lines that makes sense. One thing about the triangle inequality theorem that also is true is that the sum of your two smaller sides should always be greater than your third side. So 12 plus 19.7 has to be greater than 20.2. Just another small thing to make mention of. And another reason to talk about how doubling an angle shouldn't make the side opposite get doubled. Because you can't have a 170 degree angle measure right here thwart two 5-degree angle measures right here and be 34 times larger, because this side couldn't be 34 times larger than both of these sides right there. That you just wouldn't make a triangle out of that. That's not possible. Like this obtuse angle here. Okay, number 11. So the same kind of thing applies, and it does apply to obtuse angles. You can still use the same thing here. It's going to work out. We know this angle and side opposite here. If this is a side length C, this must be angle C. If this is a side B, this must be angle B. So this must be angle A and side length A. So these are the two that we do know. We can find side length C here. I'm going to go ahead and kind of do something a little different this time to shake it up. I'm going to go ahead and use the sign on top instead of on bottom, and to show you why you shouldn't do this if you're trying to find a missing side. So I'm trying to find side length C. I'm going to go ahead and do sine of C over C equals sine of A over A. So if I solve for C, a lot of people would think divide both sides by sine of 15. Let's try that and see what happens. If I divide both sides by sine of 15, you'll get C equals sine of 130 over 14 times sine of 15. And let's just see what kind of answer we get. Now, if you use this in the calculator properly, what you would have to do is make sure you wrap parentheses around your denominator, especially when you don't have a fraction thing. So here I do this, and then 14 times sine of 15 right here. So the answer that I get here is 0.21 blah, 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 blah. Now, it's possible that you can have a decimal as an answer, but something seems unreasonably small about that value when you compare it to this other side length that's 14. Yeah, it should be smaller, right? But I don't recall ever seeing something that was that accord smaller. You know what happened that was wrong was dividing both sides by sine of 15. And not to say that you can't, but the real problem is this isn't C. This is 1 over C. And people do this a lot. C never escaped the denominator. You can't just assume that as I divide by sine of 15, the C comes up to become the numerator value. It doesn't work that way. You have several steps you'd have to do to solve this thing this way. You'd have to multiply both sides. And there are magic steps that a lot of people know, which is one thing is flip these around, but which is how we should have started this anyway. But you have to multiply both sides by C to start. And now you'd have to divide both sides, or multiply both sides by 14, divide both sides by sine of 130. You can see where it becomes a mess. You can see where it becomes a mess. So that's why I'm saying that if you're solving for a missing side, use one of these. If you're solving for a missing angle, use one of these. You want to keep your variable in the numerator. Otherwise, it's a lot of steps. So let's go ahead and rewrite that. Let's do it appropriately here. We're going to go ahead and do C over the sine of 15 degrees equals 14 over sine of 130. And then you are just one step away by multiplying both sides by sine of 15. C is indeed in the numerator, and we are really just flipping this thing over from what we had previously. I'm sure I could just type 1 divided by whatever value I got in the calculator, and I should be good. Let me try that first. 1 divided by previous answer. So I'm getting 4.73. So let's see what happens when I do 14 times sine of 15 over sine of 130. Let's see if I get the same value. 4.73. So it's around 4.7. C is around 4.7. I think that makes just more sense with respect to the diagram that we have, the information that's there, the kind of triangle size that it is. That 4.7 is a good approximation there. B, oh, I thought this was 15. B, we need to find this side length here by finding that angle measure first. You know that this angle measure should be the difference of the sum of these with 180. So 180 minus 145 is 35 degrees. Sorry for the mess here. So that's a 35 degree angle measure. So we're going to have the B over sine of 35 equals, oh, well, Pinocchio knows on the 35, equals, and that's a B, not a 6, equals 14 over the sine of 130. Once again, I'm not using C's approximated value here. I'm sure you could sometimes land within that nearest tenth correctly, but attend to precision. That's one of our big math practices. So B is 14 times the sine of 35 divided by, and we're not even close to done with this video, over sine of 130, right? Okay, making sure I have the right numbers there. So 14 times sine of 35 over sine of 130. There's a whole other section on this besides just law. We're going to use law of sine still for the stuff later, but there's a whole other section we have to talk about, which is the ambiguous case of certain kinds of triangles. B is around 10.5 units in length there. Let's see if that answer makes sense. 10.5 being opposite these here. Here's the 15. Opposite that's 4.7. I was 35. 10.5. Sure. I don't see where wrong is with that one. And again, it's not a linear proportionality, so we're good. Okay, let's keep going. We have some ground to gain. If you feel good on these, awesome. We can just keep moving forward there. Let's go a little differently this time. Let's go get this angle first. This is going to be 80 plus 40 is 120. Minus from 180 is 60 degrees. And actually, you know what? Shoot, we had to do this first. We had to find the 60-degree angle measure first because we had to pick an angle and side opposite that we knew information for. See, 80 and B, I don't know side length B. 40 and A, I don't know side length A. I do need one part of an angle and side opposite in order to work any of these. So this is let's find A. A over sine of 40 equals, and let's use these two, 7 over sine of 60. And for B, it would be this, it's kind of same-ish. B over sine of 80 equals 7 over sine of 60. So there's our two setups, and as we multiply both sides by sine of 40 and sine of 80, we'll get A is 7 times sine of 40 over sine of 60. We'll approximate that in a second. And then B is 7 times sine of 80 over sine of 60. Okay. So here we go. 7 times sine of 40 over sine of 60 is 5.2, around 5.2 units there. And then sine of 80, 7 times sine of 80 over sine of 60. Hold on. 7.96. That rounds up to about 8.0. 8.0. So that's 8. And this is 5.2. All right, make sure the answers make sense here. 8's the longest side, opposite the largest angle. 7's the medium side, opposite the medium angle. And 5.2 is the smallest, opposite the smallest angle. Makes enough sense to me to move forward. Math teacher trusts his math work. That's always a good positive to do. Okay, two more here. We do have, we only have the known side length 18, so we are going to have to, here's the angle opposite it right here, and that tiny one. How tiny is it? It's actually 10 degrees. 150 plus 20 is 170. 180 minus 170 is 10. So there's the 10-degree angle measure. We're going to use these two. Let's find A and B the same exact way. Maybe you don't have to write out the same thing the same way. Maybe you're good at the whole, let's say this part out loud. A over sine of 150 is 18 over sine of 10. That sine of 150 has to multiply to the other side. So let's see if we can do that in our head. Suddenly, I don't know if I can. 18 over sine of 10, 18 times sine of 150 over sine of 10. That might be a lot for you guys to take in. I don't know. It's even a little bit hard for me, so that's why I say it might be for you guys. If B over sine of 20 is 18 over sine of 10, multiply both sides by that sine of 20. 18 times sine of 20 over sine of 10. I do believe that that's what those values should be as we approximate them. Let's go ahead and check out what they are. I feel like for me, a part of it is, time saving. We have a lot more things to do in this section. So over sine of 10, give me a moment as I type these things in. So this one here will be 51.8 units here. I mean, it's a big angle. 51.8 units. As this one's already 18, I believe it. The other was sine of 20 instead of 150 there. So 20. And this will be 35.4. Still believable. More than the 18, right? Almost double, as it's kind of double the angle there. Kind of surprised. So 35.4. Okay, this last one here, this is another isosceles triangle here. So whatever A is, B will also become, which is good news for us. We only have to do one of these once, excuse me, but we still have to find the angle that's on top. If these are two 80-degree angle measures, that adds to 160. 20 makes the difference between 160 and 180. So this is going to be a 20-degree angle here. We use the side opposite with it to find, to find either of these. Hiccups, I normally got to pause my video, which actually let me do here 1 second. Okay, I'm back. We'll see if the hiccups come. Okay. A and B are the same value, so I'll just go ahead and use A. A over sine of 80, or B, equals 4 over sine of 20. So A is 4 times sine of 80 over sine of 20. So is B. A is B, which is 4 times sine of 80 over sine of 20, which is going to be 4 times sine 80. 11.5. So around 11.5 units here. Okay, and those are both 11.5 there. So good. It's more than 4. Should be more than 4. I'll take it. Okay, so that's the law of sine stuff. Now, we are still going to use the law of sines in some of these other problems here, and some of them will be used in a different way. So even though you might have felt good on those ones, these have more to do to start with and more to do to finish them, because we're going to find more missing angles sometimes, as we're going to be given two sides and a missing angle. We're going to have two known sides and an angle opposite one of those sides, and we need to find the angle. Now, this is where we got to use some inverse sine, and even more than that. There's a little more to talk about here, and really wish I designed a toolkit for you beforehand here. A model airplane designer wants to design wings of the given dimensions, determine the number of different triangles that can be formed, then find all the unknown measurements, round values to the nearest tenth. So this stuff gets a little different, and I don't know how much I want to draw from the onset here. I know I really want to provide a toolkit for you. I'm sure that they're online. If you Google ambiguous case and start talking about the side-side angle rule, or as I like to call it, the angle side-side rule, because I always like to say, hey, ass, like that. I like to go like, it's the taboo thing for triangle congruence. It's one where you cannot guarantee that two triangles are congruent, where you have some known angle. And by the way, when we're talking about A, B, and measure of angle A, if this is our triangle right here, triangle ABC, the side opposite this A is A here, the side opposite this angle B is B. You're only given this angle measure, this side length, and this side length right here. This is not an included angle, it's an angle outside of these two side lengths. Angle, side, side. It's not the same as side, angle, side, like that. In a side angle side case, where two sides are known to be congruent and the included angle is congruent, those triangles are guaranteed one unique triangle congruent to each other. In an angle side side case, it is not a guarantee. Not only that, notice how they're saying determine the number of different triangles that can be formed. Sometimes you can have 2, sometimes you can have 0. In some of these circumstances, a triangle is actually not possible, and that's where the ambiguous case for triangles in the side-side angle, angle-side-side rule is going to be important. And I'll just go through these as examples to show you what some of them are. Maybe after that I can work out a toolkit for you, but I hope that the logic will kick in when I talk about. And this h, this height, this altitude will be important for some of these cases here. So here's what they're asking. Can we make any triangles out of this configuration of some plane wing sets? And if so, how many? So you have a 55-degree angle on some side length A. That is an acute angle, and that's important to mention that it's acute. I have some acute angle right here, A, which is 55 degrees. Okay? Now, the B that we refer to here is going to be a side that is attached to that angle A. So that B is going to be 9 meters in length. Let's go ahead and call this thing 9 meters. Now these two things are locked as they are. This angle measure is locked, this side length is locked. I cannot change those. This side length is allowed to be flexible and change. When I draw this other side out, even though the length will be locked at 7 meters, this angle is allowed to change with it, and if these ever connected, this angle is allowed to be flexible with it. But the question is 7 meters, this being 7 meters here, long enough that I could reach and swing this in such a way that it could hit this third side? Now, I'm not going to draw these to scale. The real question within here is, what is the shortest possible length that I can have that can reach this side? And the first answer to that is, the shortest direction I can go is perpendicularly down, right? Anything that is more this way or more this way is longer than the altitude that is drawn down, which is this h. And the h will only matter if this angle is acute. So the real question is, how long would h have to be given that you had a 55-degree angle measure with a 9 meter, in essence, a hypotenuse of this right triangle here? How long would h have to be, and is 7 longer than it, or 7 equal to it? If 7 is not longer than it, if a is less than h in this acute angle scenario, then no triangles can be formed. If a equals h, then only one triangle can be formed. It's only a right triangle case. Now we'll talk about those if we get into those. First let's see if a is actually less than h. How do you find h? Well, you use sine. This whole thing is regarding sine. The sine of 55 degrees equals opposite h over hypotenuse 9. Multiply both sides by 9, h is 9 times the sine of 55 degrees. The moment of truth will come in the calculator. When I use the calculator to type 9 times sine of 55, if it's more than 7, then 7's not long enough, I can't make a triangle out of it. It's not really in fact, it's less work to do for me. If it's equal to 7, which I tell you it won't be equal to 7 because this will be an irrational value, but if it was equal to 7, the only possible triangle I could be forming is that this was 7, and boom, that would be just this one right triangle, and we'd find some missing sides. If the height is less than 7, though, then that means that I can definitely connect this 7 and make a triangle of some sort, or possibly more than one, which we'll probably get into. But what is 9 times the sine of 55? Let's check it out. 9 times the sine of 55 is 7.37, around 7.4. 7.4 meters. What does that tell us? What that tells us is that if the altitude, the shortest possible, I'm going to write 7.37. You really need the whole exact thing. Your value needs to be more than this. If it was 7.3, it's not enough. If it's 7.3623, it's not enough. It needs to be more than this. If your value is not more than this, which ours is not, that means that this can't reach down to make this triangle here. This is 7, this is 7, this is 7.37. It's not enough. Right there, a is less than h. No triangles are possible to be formed with this configuration in this scenario. And that's part of what you're going to be testing here. So h, if you were, and I'm not one of those memorizing folks here, but when you look at this thing, it's the whole thing is the sine of this a is going to be h over b. So h is b times the sine of a. That's not one really for me to memorize. It's better to just set up the triangle and work that thing out. I think there are a lot of missteps that can happen. Now they said find all the unknown measurements, round values to the nearest tenth. If you can't form any triangles, there are no measurements to be found. I can't connect these things together. I can't use an angle that'll make that happen. I can't make an angle out of this thing, and there's no side length that can reach. So there is no triangle that can be formed. I'm actually done with this problem. I don't think a lot of other problems are like that, but we'll see. All right, number 16. Now we have a measure of angle A. And notice that I'm attacking the angle first, 120 degrees. Now that's an obtuse angle. I have a 120 degree angle right here. And they're asking us to, with the side length B, remember the one that's actually connected with the angle A at 4 meters. This side length A here is 12 meters, the next one that comes opposite this 120 in succession here. Now remember, this side length here is very flexible, so I'll just go ahead and shorten it for now. The question is 12 meters over here enough to make a triangle for us? And remember, we can bend this angle as well too. We can be flexible, and this is clearly not drawn to scale. The 12 might even be like this. The answer is an absolute yes. I can definitely make a triangle out of this. I can bend this in such a way, say this was 12, that I could now extend this side because we have no known information about that, and I can make a triangle. Now, did this have to do with anything with some h here? No, because this angle was obtuse. There is no altitude that I need to worry about here. My only worry in this case when I have an obtuse triangle, or actually even a right triangle for that matter, is that my a value just needs to be longer than this b. You see, if a was 3 meters, 3 is too short to reach back there to make a triangle. Heck, if a is 4 meters like this, the best I can do is make a straight segment right back, and that doesn't form a triangle. It needs to be at least 4.1. 4.2, 4.3. You know what I mean? It needs to be just a little bit more than 4 to come back to this. Now you could say, hey, what if I put it over on this side? That would work. The problem is you don't use your 120 degree angle anymore. This must be a 120 degree angle in the triangle. So A needs to be more than B in this scenario, and 12 is assuredly more than 4. So as long as 12 is more than 4, A is more than B, a triangle can be formed. How many? Just one. This is the only possible triangle that can be formed, and you might still be wondering how to make more than one triangle, how it's possible to make two. We're going to see them, I think, in one of these problems here. I'll make sure to show you what that has to do with, and there's more to have to do with that. So how many triangles can be formed? One. One triangle can be formed here. Now they do want us to find the missing measurements here. Everything that's missing. So we know A, we know side length B, side length A. We don't know if opposite side length B is angle B, opposite angle B is angle C. Now these problems are different from the ones before it, and it's important that you do pay attention here because now we have to be using, in law of sines, now we're trying to find an angle measure, not a side length. I can't add angles to 180 because I only have one angle measure here. I do know angle A and side opposite. I'm going to use these. We know side length B. Let's try and find measure of angle B. This is where I'm going to be using the sines on top and the side lengths on bottom because B is my unknown variable. So here I'm going to say sine of B, over B equals sine of A over A. Now I multiply both sides by 4, the same kind of thing happens here, but I'm still another step away after this because this doesn't get B by itself, this gets the sine of B by itself. 4 times the sine of 120 over 12. And if you're ultimately daring, 4 over 12 reduces to 1/3. I'm going to go ahead and do that just because I can, because I like to see things when I can. So that's 1/3 like that. But we still have to get B by itself. And this is where, again, if you watch one of my other videos, it'll work out. You inverse sine both sides. You take the inverse sine of the sine of B, and you are left with B. And this will be the angle measure here. The inverse sine of the sine of 120 over 3, or 4 times the sine of, 4 times the sine of 130 over 12. Oh, 120 over 12 if you kept those. But I'm just going to go and do that one here. The inverse sine of the sine of 120 over 3. So let's go to the calculator. Now the inverse sine button is above sine for myself. If I hit the second button right here to shift and get the modifier, inverse sine there. I still need the sine of 120 here. And divide by 3. See, the inverse sine of the sine of something cancels that out. You got to be careful when it's inside a fraction involving the 3 as well. You can't just assume it works that way. But here, this gives me not a length, but an angle measure. This is actually a degree. This B is 16.8 degrees right here. If I round that, this is 16.8 degrees. That's what we found. Okay. C, we need to find its side length and angle measure. So we need to find both of these here. Now that I have one of these, I can use it to find C. This is where other teachers might get less picky than I will for my stuff. It's up to what you want to do. Now here's the thing. If I'm just doing a single rounded value, because remember this is rounded. It was really 16.7786 something. But if I'm only using a single rounded value in an addition or subtraction, then I can happily use that to get a rounded value here. The rounded value will always be the same. There will be no change. In other words, the measure of angle C equaling 180 minus the sum of 120 plus 16.8. Yes, this is a rounded value here, but I can use this rounded number to get this rounded number here because I'm only doing a single addition or subtraction of a rounded value. It's not a multiplication, it's not raised to an exponent, it's not the sign of it, and it's only one of them. So this should be fine. 180 minus, great, 136.8 is 43, I don't want to be wrong, I think it's 43.2. 180 minus 120 plus 16.8, I can't believe I'm doing this. 43.2. So it's 43.2 degrees for the measure of angle C. So that's 43.2. Now remember, that is rounded. It's correctly rounded, but it is rounded. When I find side length C, I'm not going to use 43.2 in my calculator. I will use the calculated value coming from the 16.77 blah, blah, blah value that I got exactly. That's me being picky. I'm sure that if you round this thing that you're probably going to be on the same nearest 10th value. You might be 0.1 off, and if you are, that's important to note that that's why I'm going to use the exact value. But you might be exact regardless. So here we go. I'm still going to write 43.2 when I do this. We'll do c over the sine of 43.2 equals, let's not use this one though. Let's use 12 over the sine of 120. And so c will equal 12 times the sine of 43.2 over the sine of 120. Okay, let's see what that rounds to. So when I go to the calculator here, now I started by doing the rounded bit. Where's my button? I started by doing the rounded bit there, you can see. But let's go back. Let's recall a previous answer here, this one. I'm going to add that with my 120 and subtract that from 180 to get the exact version of that answer we were talking about here. So there's the exact one, 43.22, blah, blah, blah. That's close to 43.2, right? Clearly, it still rounds to it. But here's the exact one. So let's do 12 times the sine of my previous answer, 43.22, divided by sine of 120. This will be exact. And of course, we're going to round the answer, but this will be our exact one, 9.489. So 9.5. C is around 9.5 units in length. Let's see what happens if I did use 43.2. Let's see if it keeps it at 9.5 or if it goes to something different. 43.2. Yes, there's so much. I mean, there's a rounded portion, but it's so far away that I can see why some people would argue that it's fine to keep the other one. But it depends on what we're rounding to. If we're not rounding to the nearest tenth, it's a different story completely. Obviously, the answers are different. So you can see why I attend to precision. It is one of the Common Core mathematical practices, so I'm going to always stick to that when I can. All right, so those are the missing values there. We found them all in this triangle. Congrats, airplane designer. We found something for you for this airplane. Okay, let's jump to number 17. Number 17, we have an acute measure angle A. Gosh, we're almost hitting the hour mark on this one. We're hitting acute measure angle A, and I have a lot of room here, of 35 degrees. We have a B length of 10 meters, and this 9, the question is this 9, and just by me drawing it, I'm going to say hopefully yes, is this 9 meter length long enough that I can reach this, make a triangle? The real question is, how long is this altitude? And remember, the altitude matters if this angle is acute. If it's a right angle, or if it's an obtuse angle, the only question is this 9 more than 10? It's not, but that doesn't matter when it's acute. What matters is how long is this height. As long as the height is shorter than the 9, then we can reach with 9. So the height here, again, we use sine of 35. Imagine this right triangle right here. Sine of 35 is h over 10. So h is 10 times the sine of 35. So let's figure out what that is. 10 times sine of 35 is 5.73. So 5.73 meters tells us the 9 meter length is adequate. We are good. We can build a triangle. It's not right on this height here. It's out like this, something like that, and we can make this triangle. However, and here's a big however. So far we're good. Yes, we can make a triangle. Check that out. However, because that 9 is less than this 10, because it's less than 10, consider the fact that this isn't the only triangle that could be made. I can still take this thing and swing it this way. And as long as 9 is less than 10, it can fit on this side as well. There are two different triangles that can be made here. It's one of these weird, ambiguous cases of what does your triangle actually look like? And I'm going to draw two different ones here. There's this one that we see here, and then this one that we see right here. These are not the same triangle. They don't even have the same area. And furthermore, when we find their measurements, they will be different. I'm going to go and stretch it out a little bit more so I can fit things within a little more appropriately. The measurements, well, the measurements here within will be different. So it is really important that we note that two triangles are possible to be formed so long as, which is true, so long as this 9 was more than the altitude but less than this 10 right here. If it was equal to the 10 or more than the 10, suddenly when you swing it back, it either hits here or further out and you can't do it. I think we talked about that not in this problem. No, we didn't talk about it yet. Well, I brought up something similar right here. As long as it was equal to or more, it didn't really work. Two triangles can be formed. These are the two. Two possible triangles in an angle side case. So two triangles. Now, you are being asked to solve the triangles, to find the missing parts. There are two triangles to do this with. So let's go to work. We got some work to do. So this was A and side opposite A. This was side B, and its angle opposite is going to be B. And here's C and C. And then we're going to do the same thing here. A, B, B, C, C. Okay, we have some work to do. Let's start with the top one. In the top one here, we're going to do the same thing as we did before. Let's find the measure of angle B here. So sine of B over B equals sine of A over A. Side length A. So we multiply both sides by that, and then we'll take inverse sine. So 10 times sine of 35 over 9. The inverse sine, if I take the inverse sine of both sides, you'll get B is the inverse sine of 10 times sine of 35 over 9. Like that. Give me 1 second. Oh, that's right, because we reduced the fraction. Okay. Sorry. So the inverse sine of 10 times the sine of 35 all divided by 9 is 39.59 degrees, or around 39.6 degrees. Now, you know me, I'm going to keep that other value at bay when it comes to doing the sine of C. It's not going to change your answer. Or maybe it can. I don't know. I'm just being picky. Now, 35 plus 39.6, 180 minus that. I'm going to go do this on the calculator here because I'm using the exact value still. So plus 35 and then 180 minus that number. We're going to round this number for the measure of angle C to 105.4 degrees here. So this is 105.4 degrees. So to find C, let's use the whole A over sine A, etc., but with C now. So C over sine of 105.4 degrees equals A over sine of 35 degrees. Now, as an airplane designer, all the exact numbers would have been most important for us. So don't blame me when I try to use the exact numbers on these. I apologize if you feel like that's not to your liking or that's overkill. But if you were an architect building a plane, I mean, I don't want that plane to crash. I want to make sure that's as exact as possible. So I'm not actually using 105.4. I'm using 105.40. I'm using this number here. 105.408. So I'm going to do 9 times the sine of that previous value divided by sine of 35. And that's going to give me 15.1. So it's about 15.1 units in length. Meters. So, okay. So 15.1 meters. All right, I think we solved that triangle there as well. We got all those, and I trust it. This was a larger angle than those two. It's a longer side, and 10 plus 9 still be more than 15.1. I think everything worked out, and we have the units down. All right, now, we're not done with the problem. We're done with that triangle. We still have one more triangle here to do in this problem. And the question for you will become, how do we solve this any more differently? I mean, what did we set up in the previous one? We had we had angle A and side length A. We have side length B. We had to find angle B. We just did the same thing right here. These numbers are the same. 35, 9, and 10 had to find B. 35, 9, and 10 had to find B. What's going to be different? How do we find this thing? How did we find this B in the first place here? Remember? How did we find this one? We used inverse sine. Well, here's the thing. The inverse sine of something will only output one value for you. It's a function like any other function. It functions in the way that you put an input, there's only one output generated. But we learned that there are some values that if you take the sine, say that this wasn't 39.6, say that it was 40 for a second. Let's go to the calculator for a second. This is a big teaching moment. We learned that the sine of an angle, like 40, should equal the same as the sine of its supplement. 40 supplement is 140. So the sine of 40 and sine of 140 are the same value. They should be. So if we took the inverse sine of one of these, if I take the inverse sine right now of this previous value, will I get 40 or 140? I'm going to get 40. how do I get my calculator to get the other one? Well, the answer is you can't. The calculator only knows inverse sine as any number between negative 90 and positive 90. It only goes through those. I don't even know if it includes negative 90, but it only goes between those two sets. Okay, you can't get. It might do negative 90, but anyway, yes, I think it does. Anyway, it only goes between those two sets, and why negatives? We're not going to talk about that. But the point is, it's not going to give you obtuse angle measures. But what you know is that the sine of an angle is the same as the sine of its supplement. So this will be important for this. What's important to note is this angle is actually the supplement of this angle right here that we found. That it's 180 minus this one. This is 180 minus 39.6. And I'll show you why here in just a moment. But that's going to be, and I'm going to use the exact answer stuff again, right? I'm going to recall these things, but it's, hold on, I'm going to go and recall it right now. Let me go and find it. We typed a couple things out, so I have to go track it down again. I think it would have been faster for me to type all this out again. 180 minus this. It's going to round to 140.4 degrees. I should have known that. 140.4 degrees right there. So the sine of 140.4 and the sine of 39.6 are the same thing, but you couldn't find this number in your calculator except being its supplement. Now, how do I know that it is the supplement besides us knowing that the sines of those two are the same? Well, if we did swing that 9 meters this way, right, we talked about kind of swinging one way or the other like this, then this would be a 9, right? This would be a 9, this would be a 9. Well, what kind of triangle has these two 9s in it? An isosceles triangle. And an isosceles triangle, not just these two sides are congruent, but the base angles would have been congruent. This would have been 39.6, which means this guy right here is the supplement of 39.6. And as we mentioned, those supplements are going to get the same sine value, or the same value is the same result. So that is 140.4 degrees. Big teaching moment there. It is important for you to note that that's how we find that thing. I know that I spent minutes upon minutes teaching that one, but that's important for you to note. And guess what? It's going to change all the other values as a result of this. 140.4 degrees changes your angle C. It's not going to be the same kind of angle. It's not the supplement of this thing. It's going to be way different. Now that this is 140.4, let's find angle C by doing 180 minus 140.4 plus 35. And of course, I'm going to use my exact value there. I'll write the rounded one though. Which is previous answer plus, it's going to be small, very small, 4.59, about 4.6 degrees. Very much not the supplement of 105.4 degrees. Those don't add to 180. So now to find C, we're going to be using that 4.6 in turn. So C over sine of 4.6, or whatever exact value I have, the 4.59 value, equals, let's use A's values, 9 over sine of 35. So that becomes C is 9 times the sine of 4.6 over the sine of 35. Okay, so 9 times the sine, and I have my 4.59-ish value, over sine of 35. It's getting me 1.256, so around 1.3. 1.3 meters. And that is clearly a different looking triangle. Different area, different everything like that, right? These are definitely different areas. Different kind of setup than what we were talking about before. But two different triangle configurations are possible with the 10 and 9. Here's one, and that's what the other lengths would be. Okay, that is number 17. Whew, that was a long one. All right, number 18. Let's just rewrite the information down here. A is 7 meters. B is that a 5? 5 meters. And measure of angle A is 45 degrees. All right, it's another acute angle here. So right here with an acute angle, we are trying to determine, can we make a triangle? How many triangles can we make? And then we'll solve the triangles if we can make any. So I have a 45 degree angle measure here on measure of angle A. This B is locked at a 5 meters here. Now this A, side opposite angle A, is 7 meters. Already off the bat, we should be able to say triangle's possible. It's definitely more than any altitude here, as it's already more than this B right here. This is way more than possible. As long as if A is greater than B, you're going to be able to only make one triangle. It doesn't matter if this angle's obtuse or acute. Once it's more, that's it, right? So we can definitely make a triangle out of this, and only one of them. Unlike the previous value where we talked about swinging this thing over, if I swing 7 over, it's just too long to preserve the 45-degree angle and make a triangle. Only one triangle is possible. No H is needed to test. We know where we're at here. One triangle. Okay, now let's solve the rest of this triangle here by trying to find out angle measure B, angle measure C, and side length C. Angle measure B, so we've done some of this now before. Where am I? Sine of B over B equals sine of A, and I know sine of 45 exactly, over A. So we multiply both sides by 5, and then we will inverse sine both sides. 5 times sine of 45 over 7. And so B is the inverse sine of 5 times the sine of 45 over 7. Okay. Permit me, as I use the calculator here, inverse sine of 5 times sine of 45 over 7. Man, I gave my students a lot of work. 30.3 degrees about. You know me, I'm going to use the exact one. But 30.3 degrees about. So angle C's measure is the 45 plus that, and 180 minus that. So 180 minus that whole shindig is 104.7 degrees, give or take. It's a 104.66. 104.7 degrees. Side length C is last to be done using law of sines here. C over sine of 104.7 equals, let's use A's, 7 over sine of 45. So C is 7 times sine of 104.7 over sine of 45, which is about, how many meters? 7 times sine of 104.7 divided by sine of 45. 9.6 meters about. Hopefully you got the same thing as you tried it out. Yeah, you know, I still have a few more problems to do. I got 3 more problems to do, I think. But these, since I'm spending a lot of time teaching it, it's making the video very long. Generally, these would go a little faster. There are parts where you'll know how to skip trying to write things out in law of sines, but all that explanation stuff is very, very important for you to get these. Okay, last 3. Space travel. 2 radio towers that are 50 miles apart track a satellite in orbit. The first tower's signal makes a 76-degree angle between the ground and satellite. Second tower forms an 80.5-degree angle. How far is the satellite from each tower? So we basically need a tower A opposite side length A, tower B opposite side length B. We need these 2 values here. So we can use the law of sines for it. But this isn't enough information in and of itself. I can't do A over sine of A equals B over sine of B because that's 2 unknown variables. We need to instead incorporate something with C if we can. And we have enough information for both parts of C. 2 radio towers are 50 miles apart. These are 50 miles apart. That's side length C's thing opposite the angle. And the angle measure can be found by finding this plus this and 180 minus that whole thing. So 180 minus 76 plus 80, plus 80.5 is, I don't want to be wrong, 180 minus, I just want to take less time, 80.5, 23.5, and that's exact. So 23.5 degrees right there. Right there. We need to find A and B. We can do the same thing when it comes to law of sines. Why don't I just do one, and writing out the other should be a cinch as we're going to multiply by the sine of the other thing. So let's start with A. A over the sine of A equals C over the sine of C. So when I multiply both sides by sine of 76, I'll do A equals 50 times sine of 76 over sine of 23.5. When we do B, it will be the same thing, except instead of sine of 76, it'll be sine of 80.5. So B equals 50 times sine of 80.5 over sine of 23.5. So I'll get those two values for you here momentarily. Let me type them in. 50 times sine of 76 over sine of 23.5. I'm getting 121. What are these? Well, what are the units? Miles. 121. Do they say what to round to? I'll just do nearest tenth. 121.7 miles. B's value, instead of 76, let's do 80.5. 80.5. 123.7 miles. So B is 123.7 miles approximately there. B should be just a little larger as the angle's a little bit longer there. There's the answer both. How could you determine how far above Earth the satellite is? What is the satellite's altitude? Well, I'm guessing the tower, the ground, etc. I know that Earth isn't flat, but I guess we're working a little less curvature here on these 50 miles. We basically got to find out what the direct distance is from the satellite to the ground right here. We got to find this H guy right here, right? That height. Now, we're going to have to use one of these rounded, right? These are both rounded. We're going to have to use one of these rounded values to do it. Either way, we should get the exact same answer if you used one or the other. So I could either say how the sine of 76 equals H over B. B is 123.7. We could say H is 123.7 times the sine of 76. Remember, 123.7 is rounded. And same over here, we could say sine of 80.5 equals H over A being 121.7, also rounded. H is 121.7 times the sine of 80.5. Whichever one you do, you should get the exact same answer out, assuming you didn't use the rounded values there. So I'll show you both here. I already have B's answer kind of pre-made, so I'll go and use that one. So that one times the sine of 76 should give us, that previous value, times the sine times the sine of 76 should give us this value here, 119.99. So 120 miles. 120 miles if we rounded that to 120.0, right? Let's see if we get the exact same number doing the other one. Let's do previous entry, not that one. That one, I think. That was, sorry, I'm looking at my screen. That was for the B, A, whatever, whichever one it was. We're going to do the other one now. We're going to do the sine of 76 one. So let's do 121. Hold on. I want to make sure I typed the right values. I'm sorry. I did 123 times sine of 76, right? Okay, I did that one. Now let's do 121 times sine of 80.5. Okay, sorry about that. That previous answer times sine of 80.5, the exact same value. So you can see both of those are identical to each other. Regardless, you're getting 120 miles. Cool. So you should get the exact same one we do. How can you determine? Use the sine stuff we did. Draw the altitude, make a right triangle. All right, two more. Biology. The dorsal fin of a shark forms an obtuse triangle with these measurements. Find the missing measurements. Determine if another triangle can be formed. So straight up, I'm going to tell you that with these measurements locked, this is an angle side angle case. This is an angle side side. We have an angle side angle, and in those cases, there's only one triangle that can be formed. I'll just tell you right now, only one. There's nothing else that can morph these in such another way that they don't meet exactly at that point B. They just have to. So let's find out what these other lengths are. Now let's start by finding the measure of angle B so we can have angle and side opposite and use those to find these measures here. So 180, I should do this without a calculator, minus the sum of 27 plus 123 is, 27 plus 123 is 150, so it's 30. So this is a 30-degree angle measure here. So now when we find, say, side length A, we'll do A over sine of A equals B over sine of B. Sine of 30 is exactly 1/2, just so you know. But We'll get to that later. So 0.4 times sine of 27 over sine of 30. So 0.4 times sine of 27 over 1/2 over sine of 30. 0.363. At first, and I'm going to go to, I guess, to the nearest, well, do I want to go to the nearest tenth? What do they say? They don't say. Because then that's 0.4 again. And that's kind of, you know, they're not the same. It's not an isosceles triangle. I'm going to write 0.36 meters. Just a little smaller as it should be. 0.36 meters. Okay. Now I'm going to use the b values again to find c. C should be the same bits, only multiplied by sine of 123. So c should be 0.4 times sine of 123 over sine of 30. So c should be longer. Not longer than like 0.7. The longest it can be is around like 0.7-ish probably. So 0.4 times the sine of 123 over sine of 30 is 0.67. So let's just do that. 0.67. What was about a shark? The dorsal fin of a shark. So 0.67. There. All right, we found our values there. And no other triangle can be formed. We have an angle side angle case here. Not an angle side side or side side angle, whatever. No, even if so, if this was an obtuse angle for these, an angle side side case, as long as that one triangle can be formed, that's also it. Unless that's not the angle that's known. If we knew these 3 bits of information, yeah, we could have formed another triangle that would have spanned out that way, like we saw before. Okay, but that's not this. Last one. As a ship approaches the dock, it forms a 70-degree angle between the dock and the lighthouse. Fantastic. At the lighthouse, an 80-degree angle is formed between the dock and the ship. How far is the ship from the dock? Hickory dickory dock. We need, how far is the ship from the dock? We need this. We need C. You don't need anything for dock's angle or the distance from ship to lighthouse. We have all the information that we need to get what we need to get. We'll find C with C over sine of C equals whatever over sine of whatever. 5 over sine of 70. Okay. This one's the easiest of the problems. C is 5 times the sine of 80 over the sine of 70. Let's solve it, and we'll be done. And this is going to be a miles answer. So 5 times the sine of 80 over sine of 70. We are going to get 5.24005. I'll give the 5.24. 5.24 miles. That's how far this guy is from the dock. All right, you got a few more miles to travel there, my sir. That is more than 5. That's expected because 80 is more than 70 there. Okay, guys, and that is it. That was a very long one for a single assignment thing there. I'm sure I could have cut out half the problems and we would have been just fine. I think the ambiguous case was important to look at all those because all the special unique triangles that can be formed, maybe not solving them all for you, but hopefully you fast forwarded enough to figure some things out. All right, that'll do it for this one, guys. This is Mr. Robinson. Thank you so much for watching and take care. I will see you in the next one.